Good evening. Let's start today's session, I think. Okay, am I audible?
Yes, ma'am.
Okay, thank you. Okay, so we will slowly start the session. Let others join by that time. Okay, in the week 4, actually, we have covered a lot of concepts. So I'm thinking to just recall all the concepts that has covered in the week 4. So starting from the cosets, we will cover till fields. We will just go through the definitions and the important theorems without any proof. And for the 10-20 minutes, we will revise the concepts and then we will do the questions. Okay. So you might have already gone through the contents, but we will just revise the concept now, a quick revision. Okay. So first one is cosets. What was the coset? If G is a group and H is a subgroup of G, then AH equal to set of all AH such that H in H, where A is an element of G. Okay, so these are all the left cosets of H in G. In the same way, we have defined the right cosets also. Okay. Now, the first theorem is, if G is a group, and H is a subgroup of G, and suppose we are taking an element from G minus H, an element of G which is not in H, then AH intersection H equal to empty. Okay, so if we are taking A from H itself, then AH and H will be equal. If we are taking A outside H, then this AH and the H will not intersect. There will be no common elements. And in general, what they are saying is, if H is a subgroup of G and two elements are in G, we have only two possibilities. Then either AH equal to BH or AH intersection BH equals empty. Okay, so I am not going to the proof of all these things. The thing what they are saying is, if we have a group and a subgroup, and if we are considering all the left cosets, actually this theorem will hold for the right cosets also. Okay, so we have only two possibilities. Either both these cosets are same or they are disjoint. Okay. Now, this theorem is important. Next theorem is important in the sense to find like two cosets are same or not. Like if I am having AH and BH, either it can be same or intersection is empty. So the next theorem is used to see whether they are same or not. H is a subgroup of G, then AH equal to BH if and only if A inverse B belongs to H. Okay, H equal to BH if and only if A inverse B belongs to H. So if you want the proof, just refer the videos later. Now, using this actually we can have a equivalence relation on the set of all cosets. So how the equivalence relation will come means, if we have a group G and a subgroup, some H is there. Okay, now if we are doing collection of all AH, okay, if we are collecting all collections, what we will get? Either we will get H itself. If we are choosing A from H itself, then AH will be H. Okay, if we are choosing A outside, then we will get another, say A1H. Okay, and the next thing will be A2H. So each of this will be distinct. Okay, H is a subgroup, the cosets, other cosets need not be a subgroup. But it is a disjoint connection. Okay, A3H, A4H, A5H. Okay, so this will be a disjoint collection and union of all this H union, A1H union, etc. A5H. It will be the whole G. So all the collection of cosets corresponding to one subgroup H covers actually the whole G. Okay, and this is actually a disjoint collection. And how actually the equivalence relation. So these classes are obtained as an equivalent classes. How this equivalence relation is obtained? Okay, what is the underlying equivalence relation? That also we will recall. If A and B in G, then A is related to B if and only if A inverse B belongs to H. This is same as the earlier theorem AH equal to BH. Okay, so this is the equivalence relation. Corresponding to this equivalence relation, we can get a distinct equivalent classes as given in this figure. Now the next important result is cardinality of AH and cardinality of BH will be equal. If it is finite, say if H has some 5 elements, AH will also have 5 elements. BH will also have 5 elements. Okay. And one important theorem is Lagrange's theorem. Can anyone tell what is Lagrange's theorem? It is very useful in problems. Anyone knows what is Lagrange's theorem? If G star is a group and H is a subgroup of G, okay, in this case we can say finite group. Okay, finite group and H is a subgroup of G, then order of H divides order of G. Okay, whatever the subgroup we are taking, order of the subgroup divides the order of G. Why I am taking finite means for infinite we cannot do this kind of division. Okay, so that is the Lagrange's theorem. In the same way, whatever we have defined for the left coset, we have right coset, which will be defined as HA set of all HA such that H in H. Okay, this is the right coset. All the theorem that we have seen in the earlier, like in the case of left coset, will follow here also. Okay, in the same way. Okay, now the next thing is number of theorem. Okay, if we have left coset and right coset, we are counting. Okay, how many distinct left cosets are there, that many number of right cosets will also be there. Okay, if we are getting a group G, a subgroup H, the cosets of H in G is 5 suppose, then cosets of if left cosets of H in G is 5, then right cosets of H in G is also 5. Okay, that is what this theorem says. Now, what is index of H in G? Anyone knows what is index of H in G? And we will denote it with GH. Okay, this is cardinality of G by cardinality of H. Okay. This is same as number of cosets or left or right. Okay. So this is the index of H in G. What exactly it means is, if we have said told earlier, this is our whole G. Okay, we have this H here. Suppose G is a finite group. Again, we have some AH here, some BH here. Suppose CH and DH. Okay, so total we have 5 cosets: H, AH, BH, CH and DH. So this 5, okay, this 5 is actually the index of G in H here, the number of cosets. Okay. Now we will see what is a normal subgroup. If G is a group and H is a subgroup of G, then H is said to be normal. It is a normal subgroup of G if AH and HA are same. That means we are considering the left coset and right coset. Okay, left cosets, some particular left coset AH, it is same as HA for some particular element for every A. Okay, in this case we will say H is a normal subgroup of G. Now we will usually denote this with H is a, like this we will denote. This is the notation of normal subgroup. If H is a normal subgroup, this is the notation. Now test for normality. So if you are getting a subgroup, so it may not be easy to find whether H equal to HA for all A, and like we will have so many A in the group, right? So in that case we have a very simple way, a simple theorem to see whether a given subgroup is a normal subgroup of given group or not. Okay, for that let G star is a group and H is a subgroup of G. So this is the notation. This less than or equal to notation is just for subgroup. Okay, now H is normal subgroup of G if and only XH X inverse belongs to H for all X in G. That means if we are taking any element, this H is coming from H. Okay, if we are taking any element H and if we are able to prove XH X inverse belongs to H for every X in G, then we will say it is normal. Conversely, if it is normal, this condition XH X inverse belongs to H is satisfied. So when we come to the problem, if we are having a question to check the normal, whether a group is normal or not, what we will do, we will simply use this condition. That is enough. Okay. Okay, there is a quotient group, a factor group. We will leave this now. Okay, one theorem is there. If H and K are, if H is a norm, if H and K are normal subgroup of G, then H intersection K is also a normal subgroup of G. Okay. Okay, now we will go to the other definitions, that is our rings, integral domain, field and all. So it might be a little confusing for having this many definitions and all, but after like so many times if you are revising and all, you will be used to those things. Now first we will start with the rings. Okay, so what is a ring? Ring will have two operations, plus and addition and multiplication we can say. Okay, plus operation, one dot operation. Okay, now this R plus dot is a ring. First of all, it should be R plus. What is R plus? R plus should be a group, not just group, it is a commutative group. So it is an abelian group. What does that mean? It should satisfy the closure property, associativity, existence of identity, existence of inverse, and also it should be commutative. First condition is that one. And the second condition is R with the dot. It should be a semi-group. Semi-group means the closure property and associativity. These two should be true. R with the operation dot. Now distributive law. Left and right distributive law should be satisfied. Okay, one I will write A plus B dot C equal to AC plus BC. A dot C plus B dot C. Okay, like this the other one A into B plus C equal to AB plus AC. So these two distributive law should be satisfied. In that case we will say it is a ring. Okay. Now what is a commutative ring? If this operation we have seen R plus is an abelian group, that is plus is commutative operation, but R dot is semi-group means we proved we have the condition closure property and associativity, but we don't know whether this dot is commutative or not. In case dot is commutative, okay, if the multiplication is also commutative along with addition, in that case we will say R plus if dot is commutative, then R plus dot is a commutative ring. Okay, commutative ring means multiplication is commutative, not addition. Addition is always commutative in a ring. Now ring with an identity element. So here we have seen R plus is an abelian group means it has an identity element under addition. But since R dot is a semi group, it may not be having the identity element. Okay, if the multiplication has an identity element, in that case we will say this ring has an identity element. Ring is with a unity. R has identity if identity for dot operation exists. Okay, now ring with the unity. This unity means the multiplicative identity. We told like there is an identity with respect to multiplication, that is multiplicative identity. So that element is the unity. Okay, so if it exists we will call R is a ring with the unity. Okay, now the next is divisors of 0. If A is an element in R plus dot is again a ring. If A is an element in R, if there exists a B non-zero, again A is a non-zero element in R. A is a non-zero element in R. Okay, 0 means the identity in the addition. Okay, 1 we will say always identity in the multiplication. 0 is the notation for identity in the addition. If A is in R and there exists a B non-zero such that A dot B equal to 0, okay, in that case we will say it has a divisor of 0. Okay, A and B are divisors of 0. Okay, when we go to the problems and all, these things will be more clear. Now we will just quickly define what is integral domain and field. Okay, again we will start with R plus dot. Okay, this is called an integral domain. First of all, it should be a commutative ring with unity. Commutative ring means multiplication is commutative and for the multiplication operation there exists an identity element. Okay. Commutative ring with the unity. no zero divisors. What does that mean? Here what we told divisors of 0 means non-zero a and b such that it multiplied will give the 0. Okay, such a case should not exist. That means if we have a dot b equal to 0, either a should be equal to 0 or b should be equal to 0. In that case we will say there is no zero divisors. That is the integral domain. Now we will say what is field, and then we will stop this revision and we will go to the questions. Okay, so again field you will we will denote with the f plus dot. It is a field. First of all, it should be an integral domain. Okay, this is an integral domain means it should be a commutative ring with unity and it should not have any zero divisors. And the second one is there should exist a multiplicative inverse. Okay, existence of multiplicative inverse. Okay, till now we have told up to integral domain we were having a unit element for multiplication. Okay, so we should have for any a there should exist some b such that a dot b equal to 1, the unit element under the multiplication. So if condition is satisfied, then it is a field. Field is a very strong condition. Now we will go to the questions. I hope like you have revised all the concept and now you will be able to go through the question very quickly. First one is a very easy question. Question is, which of the following statement are true? Let us see. What is the given condition? G star is a group and D star is a subgroup of G. Okay, and it is saying D star is a normal subgroup if AD equal to DA for all A. Can anyone tell this is true or not? This is a very trivial condition. It comes from a theorem. Yeah, this is true because this is the definition of normality. There is nothing to think much. This is just the definition of normal. And so we can say A is true. By definition itself it is true. Now the second one is, if G star is a group and D star is a subgroup, then D star is a normal subgroup if and only if XD X inverse belongs to D. For all X in G and D in D. What about this one? Again this is coming from a theorem. Yeah, this is also coming from a theorem. This is the test for normality actually. I have stated already. If G is a group and D is a normal subgroup of G, this is true if and only if XD X inverse belongs to D. Okay, that's also just the theorem. Now the next question is, union of two normal subgroup is always a normal subgroup. Is this true? Normal subgroup we are taking and taking the union, whether this will be a normal subgroup or not. Leave about the subgroup normality condition. If I am taking two subgroup of a group, whether it will be a subgroup first of all? No, right? Okay, we can give the example there. First of all, B is also true. And what about C? C, what we are saying is, if we are taking two subgroups, question is if we are taking two normal subgroup, whether the union is normal subgroup or not. But if we are taking two normal subgroup, it need not be, its union need not be a group itself. For example, if I am taking 2Z and 3Z, both are subgroups of Z under addition. Okay. Now what is the union? 2Z union 3Z. It is not a group actually. Okay, it is not a group. Why it is not a group? For example, 2 belongs to 2Z and 3 belongs to 3Z and 2 plus 3 equal to 5, that does not belongs to the union. Under addition, it is not closed. Okay, in that case, this is union is not a group. Is not a group. So no need to check about the normality. So not a normal subgroup also. Now, in case if the union is a group, suppose in some condition, if the union is a group, then what about the normality? Like H1, H2 are two normal subgroups, and suppose H1 union H2 is a H1 union H2 is a group. In that case, whether it will be normal or not. Okay, that you can do it as an exercise. In which case, the basic thing we need to check is, in this case is, if we are taking two subgroups and the union is again a subgroup. Okay, under what condition the union will become a subgroup? If H1, H2 are two normal subgroups and H1 union H2 is a group, then whether H1 union H2 is normal. This is the question. This is a very easy question. The only thing is you need to see what is the H1 union H2. Okay, under what condition H1 union H2 will become normal. So if you are able to do that, then that will easily follow whether H1 union H2 is normal or not. Okay, now we will go to the fourth option. Every subgroup of an abelian group is normal. Anyone knows the answer? B. Every subgroup of an abelian group is normal. Yeah, true. Very good. So, if G is an abelian group, what we have the condition? AB equal to BA condition is there. Now, H is any subgroup. The question is whether this subgroup is a normal subgroup or not. For that, what we need? AH should be equal to HA. This is the condition for normality. Okay. Now, what is AH? AH equal to set of all AH such that H in H. Okay. Again, A into H and H into A are same because they are basically coming from the group G, and G is an abelian group. So, what is this? AH equal to HA. Okay, both are same such that H in H. This is nothing but our H, right coset. Okay. So, left coset and right cosets are same. Then what we can conclude? H is normal. So this is happening just because the G is a abelian, because that is why we are able to write AH and HA as same. Okay. Okay, that's all the first question. Now the second question is, which of the following statement are true? First one is a field is an integral domain, and second one is a finite integral domain is a field. First one you can tell easily. What about the first one, whether it is true or not? True, because it is just the definition. First of all, field means it should be an integral domain, and every element should have, every non-zero element should have a multiplicative inverse. Okay, so from the definition itself, A is true from definition of field. Now we will move to the second one. A finite integral domain is a field. Is this true or false? In general, I am asking, leave about the finite case, whether a integral domain is a field always. Leave about the finiteness. First question is, integral domain is a field or not? In general, if it is no, what is the counterexample? No, no, very good. No, what is the counterexample? So every integral domain need not be a field. Okay, so we should have an integral domain which is not a field. Can anyone tell such an integral domain? Example is Z addition and multiplication, usual addition and multiplication. This is an integral domain. Obviously Z plus is a group we know, and ring structure also it follows, and the unity 1 is also there. Okay, so obviously, and there will be no divisor of 0. A dot b equal to 0 means either a equal to 0 or b equal to 0. Okay, so in that case it is an integral domain, but it is not a field, because for example, if I am taking an element 2, it does not have a multiplicative inverse. Like if for 2 the possible multiplicative inverse is 1 by 2. Okay, no multiplicative inverse for 2, not just for 2, for 3, 4, 5, everything. Okay, minus 2, minus 3, like that. It does not have a multiplicative inverse. So what we can say, it is not a field, but it is an integral domain. So it does not satisfy the condition of multiplicative inverse. All other things are satisfied. Now we know Z, it is an infinite set, right? Okay, in our question, it is finite integral domain. So in infinite case, it need not be true. Okay, in finite case, the question is whether a finite integral domain is a field or not. Any idea or any guess? Okay, actually this is true. In infinite case we told it is not true, but in finite case the finite integral domain is actually a field. Now to check, suppose like say r plus dot is a finite integral domain. Okay, now we need to prove that it is a field actually. Okay, so what we are having for to prove the field, first we need to prove it is an integral domain, and then we need to find the multiplicative inverse for each non-zero element. Okay, now in this case we have already got it is an integral domain. Okay, now we only need to consider the multiplicative inverse cases. Okay, for example, let me take A, which is not an element of 0. Sorry, which is not 0 element. Okay, for each non-zero element we should have a multiplicative inverse. So A not equal to 0 in R. So since it is an integral domain, it has a unity. In case if A is the unity, then it has the inverse as unity itself. Okay, now suppose if A is not a unity, if A is some other element, now what we will do is we will consider all the a power 0, a power 1, a power 2, a power 3, etc. like this. Okay, now this is actually going to be infinite collection, a0, a1, a2, a3, etc. But what we know, this is closed under multiplication. This set is actually closed under multiplication. That means this a square, a cube, all elements are basically coming from R only. So this is actually contained in the set R itself, the finite integral domain. And what is this? This is finite integral domain. Since it is finite, this is also finite. Okay, so it is not some kind of infinite thing. At some point, at some a power n, it will come as the previous a power n. Okay, that is, there exists a j greater than I such that a power I and a power j are equal. Okay, are you getting that? Suppose if every element a power m, a power not, a power 1, a power 2, a power 3, everything is distinct element, then the set is going to be infinite. But that is not true since R is a finite set itself. Okay, so there should be some element which is repeating. Okay, so we are taking such element, a power I and a power j. without loss of generality we can assume a power j is the greater number, j greater than I, such that a power I equal to a power j. Now in that case what we can do, a power j minus I equal to 1. Okay, here multiplying with a power minus I on both sides. So what is this actually? A into a power j minus I minus 1 equal to 1. Fine. What is this? A into A inverse. So this is our inverse of A. We have taken a non-zero element. We got the inverse, which becomes as 1. Correct? So for any element in R, we got a multiplicative inverse also. So this is due to the finiteness of R. Okay, so B is also true. But we got an integral domain which is finite, satisfy the multiplicative inverse property also. So we are getting all the conditions of the field, and hence a finite integral domain is a field. Okay, any doubt for anyone? I hope it is clear. If you have doubt, you can ask. Otherwise, we can move to the next question. Now, next question is, G is a group and H is a subgroup of index 2 in G. Okay. Then which of the following is true? The questions are, H is a normal subgroup of G, H is not a normal subgroup of G. Okay. Any idea? Given a subgroup with index 2. That means, what is that index we told? GH equal to 2. That is same as number of left coset or right coset, anything you can write. So H in G. Okay. So how many left cosets are there? Only 2 left cosets are there. That means some H, some AH. Okay. So all the left coset together forms a disjoint union of the group G. These many things we know. Okay. Using this concept, can you say whether this H will be a normal subgroup or not? Okay, again let me say, what is this? Number of left cosets are only 2. Okay, index is 2 means left cosets are only 2. So one is H itself, the subgroup itself. The other one will be AH. So this forms where A will be from G minus H. Why? If A is from H, then AH and H will be same, right? Okay. What is our G? G is this one and H is the subgroup. If we are taking A from H itself, AH means by the closure property, since H is a group, AH will also be here only. So we are taking an A from here and we are multiplying all the elements from H. So we will get the other collection. So this H union AH will be equal to G. We have only 2 subgroups, 2 cosets, H union AH, which is equal to G, and we know 2 distinct cosets. These are 2 distinct cosets, right? H and AH. This H intersection AH will be empty. Okay. Now the question is whether this is a normal subgroup or not. So if it is a normal subgroup, what we need? AH should be equal to HA in every case. Now if A is in H, okay, in that case what is AH? AH is H itself, right? A is in H, H is a group, so it is crossed under the multiplication, under the operation, whatever the operation. So AH should be equal to H. In the same way, HA should also be equal to H, right? What is HA? HA means set of all HA. H and A are coming from H only. Since H is a group, HA should be equal to H only. Okay? Like I am just telling only, I am not writing all the details. If you are facing any difficulty in following, please let me know. I will explain or write again. Okay. In case if A equal to H, what we got? AH and HA are equal. Both are same as the case H. Now, if A does not belongs to H, okay, then this forms the remaining part of G. H is there, AH is another part, right? If A is not in H means A is a element from G which is not in H. Okay. Now, what will be AH? AH will not be H, right? AH is the remaining part. And in the same way, what will be HA? HA cannot be H again. Okay, HA should be the other coset only. HA and AH should be equal in this case. AH cannot be HA and HA cannot be HA. So, AH and HA are the remaining part G minus H. Correct? So, AH equal to HA. That implies, so we covered all the cases when A is in H, when A is not in H. In every cases we got AH and HA are equal. Okay. In first case, this is our AH. In the second case, this is our AH or HA, both. Okay. So what we got is H is a normal subgroup. So what the question is, if we are having any group and H is a subgroup with index 2, or in case of finiteness we can say just half the element of G are in H. Okay, in that case H is always a normal subgroup. Whatever the group G and whatever the group subgroup H we are getting, if the index is 2, then H is always a normal subgroup. Okay. Okay. Now we will go to the homomorphism. Okay, I forgot to state the homomorphism while doing this. What is homomorphism? If G1 star phi is a map from G1 star to G2 dot, okay, then phi is a homomorphism if phi of x star y equal to phi of x dot phi of y. So what does this phi means? Phi is a map from G1 star to G2 star. So phi maps elements of G1 to G2. Okay. So this phi of x and phi of y are coming from G2. Phi of x and phi of y are elements of G2. So between them, what should be the operation? The operation in the G2, that is the dot operation. But x and y are coming from G1. Okay, before applying phi, we are taking x and y from G1. So here the operation is star. So what homomorphism says is, if we are applying the operation star first, then applying phi, it should be equal to phi x dot phi y from the second group. Okay, if this condition is satisfied, then phi is a homomorphism. And what is isomorphism? If this phi map is 1, 1, on 2 and homomorphism. In this case, we will tell phi is isomorphism. So this is the homomorphism and isomorphism. Now, you know what is homomorphism, and in the question it is given the function f is a homomorphism. They have given that it is a homomorphism. So we need to use the property of homomorphism to solve the question. And f is a homomorphism given from integers with addition to positive real number with multiplication, and it is given as, defined as f of m, where m is an integer, which is equal to 1 by m for all m in Z. Okay, so in this case, what is f of mn? Okay, here actually for when m equal to 0, we will have some kind of problem. So there is some small error with the question. So maybe for all m, m not equal to 0. Suppose this condition is there, so we will check for the m not equal to 0 condition only, because when m equal to 0, this, okay, sorry, that is fine there, because 1 by m is going to be an element from R plus dot, so it is not a problem. Okay. So the question is whether this is, no, the question is if f of m equal to 1 by m is defined as is given, then what is f of mn? So we need to use the condition of homomorphism here. So what we need to do is, in this part, we should write it in terms of addition, okay, plus operation, because the first group is z plus, and then we should separate that with this equation, okay, and then we should obtain what is the answer. Okay, can you just try everyone, what is f of mn, where n is an element from natural number? We just know what is the value of f of m. Okay, so we should write f of mn in terms of m only. This mn in terms of m. What is mn? Mn means m plus etc. plus m n times, right? Okay. So phi is defined from z plus 2 r plus dot. Correct? Here we have the addition operation. So phi of mn. So what we need inside this, we need the addition. Okay, m plus this addition we are taking m plus etc. plus m. How many times it should be there? N times, because n times m we are multiplying. Okay, now given phi is a homomorphism, so what should be phi of m plus m plus m plus? Can anyone tell this one? What is phi of m plus m plus? So this is the condition for homomorphism. Phi of x star y equal to phi of x dot phi of y. Okay, thus dot is coming from the second group. Here phi of m plus etc. plus m. Okay, plus is coming from the first one, and it is going to r plus under multiplication. So it should be phi of m dot etc. phi of m. Okay, so this is the operation in the G2 or r plus. So we know phi of m, it is given in the question, it is 1 by m. Okay, how many 1 by m are there? Here we have n times mm. Okay, 1 by m power, very good, 1 by m power n or 1 by m power n. So that is the answer B. Okay, this is how, if we are getting a homomorphism, we can use the condition of homomorphism to find a given function value. Now, next we will go to a question which checks whether the given groups or given set is an integral domain or not. So here the operation is not specified. So if it is not specified, you can assume it as addition modulo 7. Like, what is the standard one? In set 7 it is addition modulo 7 and multiplication is multiplication modulo 7. Okay. In set 12 also addition is addition modulo 12 and multiplication is multiplication modulo 12. And in mn of r, usual addition and multiplication of matrices. Okay, so the question is, which of the following is not an integral domain? Which of the following? Is or are? Any idea? Basically this group structure, like said 7 plus 7, that group structure will easily follow because we know already that. Okay, let us see. Suppose Z7 plus 7 we are considering, Z7 plus 7 and multiplication modulo 7. Okay, first condition is it should be a group under plus 7, set 7 plus 7. It is a group, it is very clear thing, we have already seen many times. Okay, it is a group, and also set 7 under multiplication 7, it is a semi group. That is also just the closure property. It will hold because we are using the multiplication model of 7. For example, I am taking 6 into 2 under multiplication modulo 7. What is this? Can anyone tell? 6 and 2 are coming from set 7. What is 6 into 2? Okay, if we are having, so this is just like the, yeah, very good, 5. It's just like the addition modulo 7. We will just multiply the element, it is 12. Then we will take the mod 7. Okay, mod 7 means when we are dividing with 7, what is the remainder? So this is 5. Okay, so in this way closure property is satisfied. Associativity will also hold. It is a kind of usual multiplication only. Now, the first we need ring, commutative ring with unity. Commutativity of multiplication is also an easy job. So you can verify each and every condition separately. So it will be helpful in understanding. Okay, so you separately do all the condition. I will tell the most important things only. Now again in set 7 we have a unity. Unity means 1 will be the unity. If I am taking any element x from set 7, 1x will be x. So this will form the unity for multiplication. So we got commutative set 7 plus 7 dot 7. It is a commutative ring with unity. Now we need to check whether it is having a divisor of 0 or not. So we need to check whether it is an integral domain or not. So whether it has a 0 divisor. In the same way for set 12 also. So whatever we have done here for group, semi-group, unity, commutativity of multiplication, everything similarly holds for set 12 also. So in both this case we will do together for set 7 and set 12 whether does it have a 0 divisor or not. Okay. So now again let me recall what is 0 divisor. A dot b equal to 0 with a not equal to 0 or b not equal to 0. Okay, in this case or both a b non-zero, if we are getting a dot b equal to 0, in such a case we will have it has a 0 divisor. So my question is, first we will go with the set 12. Okay, in set 12 does there exist a 0 divisor? So does there exist two elements from set 12 such that the multiplication of these two elements gives 0 and these two elements we are choosing is a non-zero element. Can anyone give me such an example of two elements from set 12 whose multiplication gives 0 but that element is not 0? 3 and 4. Okay, very good. In set 12, if I am taking 3 and 4 from set 12, what is 3 into 4? It is 12. 12 means in set 12, 12 mod 12 which is equal to 0. So we got two non-zero element whose multiplication gives 0. Okay. So in that case 3, 4 are divisors of 0. Okay. If there are divisors of 0, in the same way what we can say 2 into 6 equal to 0, right? In that case also we can say 3, 2, 4, 6. All these are divisors of 0 in case of set 12. Okay. So set 12 has divisors of 0. If there is no divisors of 0, then we will say integral domain. So in this case set 12 is not an integral domain. Okay. Now just like this case, can you say set 7 is integral domain or not? So all other conditions are fine. up to unity and commutative ring, everything is fine. Okay, you can just verify yourself that one. The only thing is whether it has a zero divisor or not. Whether any two non-zero element from set 7 can be multiplied to get a zero. That is the question here. No. Okay, good. Set 7 means it contains 0, 1, 2, 3, 4, 5, 6. So basically the thing that you need to note here is 7 is actually a prime. So 7 can be either written in terms of like 1, 7 or 7, 1. There is no other possibility. And obviously 7 is not there in set 7. So whatever the multiplication we are performing in the set 7, it is not going to give the value 7. If it is going to give either 7 or some kind of like 14, that is multiple of 7, then only we will get the remainder as 0. Okay, when it becomes a prime, always it will not be having a 0 divisor. Okay, so no 0 divisor. So set 7 is an integral domain. So in general, what we can say is, if P is a prime, set P is an integral domain. Actually this is true for field also. In case of prime, it will be field also. Okay, I am not going to the details. Okay, this is actually an if and only if condition. Okay, I am not going to prove this detail, but you will get the idea of the proof, how it is going. Now, what is set P? When P is a prime or whatever P, set P means this is up to P minus 1. So, since P is a prime, only thing possibility is 1 into P equal to P or P into 1 equal to P. Okay, no other combination if we are taking, it will be a it will not give the remainder as 0. Okay, that is why set P is always an integral domain. So we cannot say this will be equal to 0 in this case. We cannot get two non-zero element whose multiplication gives this prime number P. Then only we will get the 0 or 0 divisor. Okay, in case if P is composite. Okay, composite means it is not a prime. Okay, in that case we will have some small element. Okay, in case of set 12, what we got, 2 into 6 equal to 12. For example, I am taking set 8. What I can do, 2 into 4 equal to 12. Or set 15. Sorry, 2 into 4 equal to 8. This is 0. This is also 0 in set 12. If I am taking set 15, what we can write, 3 into 5 equal to 15, which is same as 0. Correct? So, if it is not a prime, obviously we will have some small two elements which multiplies to that element, which multiplied will give the given element. Okay. So, in that case, always we will have a divisor of 0. So, here we can see 2 and 6 are divisor of 12. 2 and 4 are divisor of set 8. 3 and 5 are divisors of set 15. So, divisors of 0 exist when P is not prime. Okay. So, in this case, set P is an integral domain if and only if P is a prime. So, why I am saying this is true for field also? Because set P is always a finite integral domain, correct? Set P is a finite integral domain, and from the earlier result, earlier we proved that every finite integral domain is a field. Every integral domain need not be a field, but finite integral domain is always a field. So we got when P is a prime, set P is a finite integral domain, so it is a field. Okay, so this result is true not just for integral domain, it is true for field also. Is that fine for everyone? Okay, again, if you have any doubt, please ask, we can clarify. Okay, good. Now let's go to the next question. G is given as the group GLNR. Okay, And okay, what is GLNR? Anyone knows? General linear group. Okay. GLNR, we will say general linear group on n letters. GLNR means set of all n by n matrices. Set of all n by n matrices such that its entry Aij's are entries of A, are coming from the real number. Since it is R, it is coming from real number. If it is C, then Aij will come from C. Okay, that is the only difference. That is why we are taking R. And this n corresponding to the order n of matrix A n by n, such that determinant of Aij, determinant of Aij is non-zero. Okay, that is set of all invertible matrices, n by n invertible matrices. That is the general linear group on n letters over R. Okay, now given G as this group, set of all invertible n by n matrices over R, and H is given as a subgroup of G. Okay, verify that H is a subgroup of G, that you can do later. Okay, for subgroup condition, you know some 2-3 conditions are there. You need to verify that condition. Given H is set of all matrices from G such that determinant of A is 1 by 3 power n. Okay, we told when determinant of A is non-zero, it is G. Now we are restricting the case determinant of A is 1 by 3 power n for any m in Z. We are collecting all such matrices from G and taking it as H. So first thing is you should verify that. That's your exercise, an easy exercise. Verify H is a subgroup. Okay, that is an easy thing. So I am leaving that to you. Now the question is whether it is a commutative subgroup, whether it is a cyclic subgroup, or whether it is a normal subgroup, or none of the above. Anyone has a guess on whether, like you can tell whether one of them is true or not true. Each of the option you can just check. The commutativity may be, it may be comparatively easy. Anyone can say whether, in general we know that matrices are not commutative, right? If I am taking two matrices AB and BA are not equal, but we are just having H only. For H we are having some condition, we are having a sub collection of matrices only. Okay, in that case we need to check whether it is commutative or not. If it is not commutative, we should be able to give two matrices which is coming from H, but it does not commute. Okay, leave about everything. What is your guess whether H will be commutative or not? Just a guess. What do you think? Yes or no? When it comes to matrices, the commutativity is actually clear, right? Whether it will be commutative. It's actually not commutative. We know matrix multiplication is also okay. Okay, I forgot to tell, this is actually coming with the matrix multiplication. GLN of R, if we are telling it is not addition, it is multiplication. Okay, so obviously under multiplication, usually it is not a like set of all matrices is not commutative under multiplication. Now we are having H only. H means we should choose two elements with a determinant of A equal to some 1 by 3 power m, and we should be able to prove that AB and BA are not equal. Okay, let me give two such elements. Okay, so I am taking A and B. What is the determinant of A and determinant of B? What is it? What is determinant of A? This is this calculation, right? Yeah, 1 by 3. Determinant of A is 1 by 3. Similarly, determinant of B is 1 by 3. Okay, so what is H? H means set of holes with the determinant of A is 1 by 3 power m for some m in Z. So m equal to 1 here, we got 1 by 3. So what we got? This both the A and B are elements of H. Okay, now we need to check whether it is a commutative group. Okay, for that we should be getting AB and BA equal or not. Okay, what is AB? AB will A into B. It is 1, 1, 1, 10 by 9, correct? And BA equal to 2. Okay, from here only you can say like first elements differs, so AB and BA are not equal. And 1 by 3. 1 by 3, 1 by 9, correct, right? Check the calculation also. Okay, here also what we got? AB and BA are not equal. Fine. And again you can consider what is determinant of AB. Determinant of AB is 10 by 9 minus 1, which is equal to 1 by 9. So this is same as determinant of A into determinant of B. Okay. The same way determinant of BA. So what is 1 by 9? This is 1 by 3 square. Again it is in the form 1 by 3 power m. So it is in H, right? So this is the closure property I am saying. So here determinant of BA also equal to 2 by 9 minus 1 by 9, which is again 1 by 9, which is same as the determinant of B into determinant of A. So this is just one example. You can choose any A and B such that A, B and BA are not equal. So this is H is not commutative. Okay. Now the next question is whether H is a cyclic subgroup or not. Okay, maybe that I will start. It may be a bit difficult. Suppose H is cyclic. Okay, what is the definition of cyclic subgroup? Give me 1 minute. What is the definition of cyclic subgroup? There exists some A in H such that A generates the whole H. Generate A, that is set of all A power n in Z. So this is equal to the whole H. In that case what we will say? H is a cyclic group. Okay. Now here the question is whether the given H is a cyclic group or not. For that, suppose it is a cyclic group. Okay, suppose H is cyclic. What we need? Then we need a matrix A. There exists a matrix A in H such that set of all A power n such that n in Z is exactly same as our H. Is this possible? What do you think? If we am taking any element from H I am taking and I am taking all the power, that means A square, A cube, all the things I am taking and corresponding inverse also, then whether this is same as H or not. Any idea? Okay. Suppose I am taking A, then obviously A is from H. So what is determinant of A? Determinant of A will be some 3 power m, where m is in Z. Okay. Now what we are doing? We are taking all the power A square, A cube, etc. For example, what will be determinant of a power n, which is equal to determinant of a into determinant of a, n times we are multiplying, right, using the property of determinant. So we will get 1 by 3 power m whole power n, correct? Okay, so what we are having is, first we are having 1 by 3 power m, then we are having 1 by 3 power m square, 1 by 3 power m cube, etc. So if we are generating the elements from a, that is a square, etc., we are getting a power n has determinant like this. But in general, other than this also, h will have some other elements. For example, if I am taking a as 1 by 3 power m 0 0 1, its determinant is 1 by 3 power m, right? But other than this, I have one element 1 0 0 1 by 3 power m. This is different from this element, but this also have determinant 1 by 3 power m. Suppose I am taking a is this element, then a generates all the element in the sense that a has 1 by 3 power n determinant, a square has 1 by 3 power m square determinant. So in that case, this is not covered in this group. Okay, in the generator of a, generator of okay, if this is a and this is b, generator of a does not contain b, correct? If what are all the elements of generator of a? It has determinant 1 by 3 power m. That 1 by 3 power m corresponds to the a element. Then 1 by 3 power m square, that is like decreasing, decreasing, decreasing. Again, we are not going to get the 1 by 3 power m. So b is not contained in the generator of a. But obviously b is an element of this H group, because b has the determinant 1 by 3 power m, right? Okay. So if I am, it is just an example, if I am taking any a with 1 by 3 power m, other than a, I have some other a dash which also has the determinant 1 by 3 power m, but it is not contained in the group H. Okay, it is not contained in the generator a. Okay, but it is contained in H. So this a, generator a, is not equal to H. Okay, this is true for all a in H. So I hope you understood the concept here. So what we can say, it is not a cyclic. If it is a cyclic, we are obtaining a contradiction. We are obtaining an element which is not generated by this A. Okay, so in this case, we can say it is not a cyclic group also. Any doubt in that one? Anyone? Okay. Now the next question is, H is a normal subgroup. This using the normality test, can you tell? We have a normality test. If H is a normal subgroup, if and only if some condition is satisfied, XH, X inverse belongs to H, right? Using that, can you tell whether it is normal or not? Take some 2 minutes and let me know whether it is a normal subgroup or not. Anyone? So our condition is H is normal if and only if XH, X inverse belongs to H, for H in H and X in G. Okay, what is our G? G is the general linear group. Okay, so we are taking any B from GLN of R, and A is an element from H, our group, with the determinant 1 by 3 power m. So for some m in Z. Now this H is normal if and only if XH X inverse belongs to H. So that means VA V inverse belongs to H. So we need to check whether this is true. If this condition is true, what we can say? It is normal. Okay. Then it is normal. Then H is normal. This condition is satisfied. So when we can say BA V inverse belongs to H? If the determinant of BA V inverse should be in some form of 1 by 3 power m. Are you getting? What is the determinant of BA V inverse? For determinant, we have the property. We can multiply like this, determinant of B. Everything is an n by n matrices, right? And the determinant of B inverse, this will be the 1 by determinant of B. Okay, this is 1 by determinant of B. Determinant of B is a non-zero value. So both will be word cancelled, and what we will get is determinant of A. So what we know? A is from H. Since A is from H, determinant of A will be in some form 1 by 3 power n. Okay, that means determinant of BA V inverse is in the form 1 by 3 power n. So what we can say? If this determinant is in this form, we can say BA V inverse is an element of H. So this is nothing but H is normal. Correct? H is a normal subgroup of G. Is that okay for all? It is just we are using. So when I stated that theorem in the beginning, I told it is like very useful theorem to check the normality. Otherwise we may not be able to say whether H equal to HA like that, right? But here just using this condition and just applying the property of determinant, we can easily say it is a normal subgroup of G. So this is the correct option. A is false, B is false, so C is the correct option, and we proved it. Okay. Now again we are going to a question which includes ring, integral domain and all. It is given R is a ring which satisfy xy square equal to x square y square for all xy in R. So the first question is whether R is a commutative ring or not. So commutative ring means already addition is commutative. So commutative ring means multiplication should be commutative. Okay. So the question is whether xy and yx are equal. The condition is given xy whole square equal to x square y square. So I just want you to expand the condition here. What is xy square? Just expand it. And what is x square y square? And expand that also. Do some suitable calculation and then you will obtain xy equal to yx. You can just try expand xy square and x square y square. Given xy square equal to x square y square. What is xy square? Multiplying xy 2 times, right? So how I can write this? xy. Okay? In the same way, what can I write in the right hand side? Can anyone tell? Instead of x square y square, how can I write? Anyone? What is in the right hand side? X square. X square means x into x, right? This is x, y. Correct? Now, the next thing is just the cancellation law we are applying. Okay? Or we are multiplying on both sides with x inverse. What we will get is, here we are multiplying with x inverse, xy, y inverse. Here also we are multiplying front with x inverse and at the end with y inverse. So x inverse x is identity and y inverse y is identity. So remaining is yx. Here also this is identity, this is identity. Remaining is xy. So what we got, xy and yx are equal, and this is true for all xy and this is true for all xy. Okay, in R. So what we got under multiplication, this is commutative. Okay, xy equal to yx under multiplication. So it is commutative. So the question was whether R is a commutative ring or not. So we got it is a commutative ring. Now the question whether it is an integral domain or not. Anyone have an idea? Just with this condition, can we say whether it is an integral domain or not? This again, it is an easy thing. I am taking Z8 under addition modulo 8, multiplication modulo 8. This is obviously it is a ring, right? We have addition operation, multiplication operator. Multiplication is commutative also. Or okay. Is this an integral domain? Is this an integral domain? If it has a divisor of 0, it is not an integral domain. Integral domain means it doesn't have a divisor of 0. Does Z8 have a divisor of 0? No. No means no for which question? Okay. Okay, not an integral domain, very good. So, for example, we can choose 2 and 4, right? 2 and 4 equal to 0 in Z8, 2 into 4. Yeah, 2 into 4 equal to 8. So, what we can say, it has a 0 divisor. 2 and 4 are 0 divisors of Z8. So, it is not an integral domain. Okay. Now, let us see. First of all, Z plus 8 multiplication 8, it is a ring that we know. And obviously, it will satisfy the given condition, right? Xy square equal to x square y square, because these are just like normal numbers from the integers. If we are multiplying like in whatever the order we are multiplying, this is going to be satisfied. Okay, so we got a set which satisfies this condition, xy square equal to x square y square, but it is not an integral domain. So R need not be an integral domain. So this is false. Okay, is that clear? It is just like I am giving a counter example. Now what about whether it is a field or not? That is a very easy question again. Can we take a set of all real numbers? Okay, if you are taking set of all real number, no, set of all real number is a field, right? All real number under addition and multiplication, it is actually a field. What is the thing? It is a ring, obviously you can see, and there is no divisor of 0. That's also a b equal to 0 means either a should be equal to 0 or b equal to 0. And also for any element x non-zero, x not equal to 0, we have 1 by x such that x into 1 by x equal to 1, and this is the unity in multiplication. Okay, so what we got? Field, R is a field actually. Okay, so set of real number, we cannot take it. Okay, what we need is, okay, you don't need to take an example here. What I can say is, here R is not an integral domain, we already got. Okay, now whether R can be a field now? If R is a field, it should be an integral domain plus multiplicative inverse is there. If R is a field, it is not an integral domain. So what we should have, R should not be a field. So this is trivially false. In case R is a field, the first condition of field is it should be an integral domain. Then it will be an integral domain. But we already proved under just this condition it need not be an integral domain. Or again we can use the same example z8 plus 8 multiplication 8. Here 0 divisor is there, so it is not a field. But it is satisfy the condition xy square equal to x square y square. Okay. So there is no use if we are taking a set which is a field already. Okay, we need to get a counter example. That's why we are choosing suitably. Okay, so yeah. So this is also done. So only thing we got, it is a commutative ring. So this is the proof also. Now here also it is very trivial thing. Can you say what is field, what is not a field in that? It is very easy question, like I already covered almost all the cases here. C plus dot means set of all complex number, addition and multiplication, usual addition and multiplication. Then rational numbers under addition and multiplication. Then integers under addition and multiplication. And set of all a plus b root 2, where a, b coming from Q. Okay, C. Okay, C is not a field. I can very quickly say about A. For A, what we got, C plus will be a group. That is the very trivial example, trivial thing to do. And C dot will be a semi group also. And we have 1 as the multiplicative identity. And also multiplication is commutative. 1 will be the multiplicative identity. And for any C in C which is non-zero, C not equal to 0, 1 by C will form the inverse under multiplication. In the same way for rational number also and also no divisors of 0. That is also in very easy to notice. In the same way Q plus dot is also a C plus dot is same way Q plus dot are field. Now what about Z plus dot? So Z plus dot also in the beginning for the so many condition will hold, the problem will come when the inverse. This is actually an integral domain also. Okay, up to divisors of 0 it is fine. The only thing is the last condition, multiplicative inverse. For example 2 in Z, the possible multiplicative inverse is 1 by 2 which is not in Z. So no multiplicative inverse. So it is not a field. Now when coming to B, since we got which is the wrong option, we got this is the wrong option. Now what we need to check is a plus b root 2 a b in Q, whether this is a field or not. That we will just do some details, not every details, very required details only. Okay, here also we can see under addition, multiplication, everything is like a normal addition and multiplication. So under addition it will become a group, and under multiplication is closure property will be satisfied. For that you can check a1 plus b1 root 2 into a2 plus b2 root 2. What is this? What we will get is a1 a2 plus 2 times b1 b2. Okay, so I am just multiplying, cross multiplying, and a2 b1 plus a1 b2 into root 2. This is again in the form of some c plus root 2 d. So this belongs to the say given set here, right? Okay, that is why the closure property is satisfied. In the same way, associativity, it is a very easy thing to do, and identity, one will act as the multiplicative identity, and also if two elements, if we are multiplying a1 plus b1 root 2 into a2 plus b2 root 2, it will not be 0. If both are non-zero, that product will not be 0. Okay, that's also very trivial to think. Now, what is the multiplicative inverse of a plus b root 2? What is this? which element when multiplied with a plus b root 2 will give 1? It is 1 by a plus b root 2, right? Okay, so a plus b root 2 into 1 by a plus b root 2 equal to 1. So the possible multiplicative identity is, multiplicative inverse is this element. So multiplicative inverse, if it exists, it should be in the given subgroup itself, or given, the question is for field. Okay, if multiplicative inverse exists, it should be in the given set or given field itself. So if this is in the field, what is the field? Field is in the form of set of all a plus b root 2. This element 1 by a plus b root 2 should also be in some form c plus root 2 d. That we need to check. Then only we can say the multiplicative inverse exists, right? So what is a plus b root 2? Whether can we write it in the form of some c plus d root 2? Okay. Here, what is a plus b root 2? We can multiply with a minus b root 2 on both the numerator and denominator. Okay, so what we will get is a minus b root 2 into a square minus b square. A plus b into a minus b is a square minus b square. So what we will get? A by a square minus 2b square plus minus b by a square. Okay, just check the calculation. If something is wrong, you can correct it. Okay, so what is this? Some form of this is c, this is d, c plus d root 2. Okay, so this is again from the given set or given field only. So we cannot just say there exists a multiplicative inverse like this, it is equal to 1. We should prove this is same, this is belongs to the given set, this is same as in the form of a plus b root 2. Okay, so for this one actually we need this much explanation to say it is a field. For everything it is else it is easy. Okay. Now the next question is, again it is a function from one group to another group. The first group is given as z under addition, and second group is given as 2z under addition. Okay. Now f is a map from I to E. It is defined as f of x equal to 2x for all x in the I. Now the question is whether f is 1, 1, on 2, whether it is isomorphism, and so on so. Okay. First question, whether it is 1, 1, yes or no? F, given f is 1, 1 or not? How we will check 1, 1? F of x1 equal to f of x2 implies x1 equal to x2. Is that true? Is the condition for 1, 1? F of x1 equal to f of x2. It should imply x1 equal to x2. Okay. Now what is the given function? F of x equal to 2x. So what is f of x1? 2x1. F of x2 is 2x2, correct? This implies 2x1 equal to 2x2. So it should imply x1 equal to x2, right? So this is a very trivial thing to verify that it is a 1, 1 mapper. Fine. Now, so A option is passed. Now we need to check whether it is on to. Can you say this is on to or not? Is this an on to map? What is on to? If we are taking any element from the codomain, that is from 2z, if I am taking any element, there should exist an element from z which maps to this element that we have chosen under the map f. Okay. So consider any element from 2z. What is the form, and which map from z will map, which element from z will map to that chosen element? For example, the element of 2z means 2z means set of all 2x such that x belongs to z. That means set of all even integers. Okay. Now I am taking an element 2x from 2z. Obviously, what is f of x? 2x belongs to 2z means x is from z, right? Okay. So see, 2 from here I am taking 2x. So here we have an x, and that x will map to f of x equal to 2x to the chosen element. If I am taking any element from 2z, I have the half of the element x which is from z, which is mapping to this 2x. So it is an on to map also. Okay, so f is a 1-1 map and on to map. So A and B are false. Now we need to check whether it is an isomorphism. Isomorphism means it should be 1-1 on to plus it should be a homomorphism also. Okay. So for that we need to check whether it is a homomorphism or not. For that what we need, f of x plus y equal to f of x plus f of y. So here I am just using the plus both side because here I have the plus operation, here I have the usual addition operation. So in both sides I can use the respective operation. So what is f of x plus y? F of x plus y, by definition it is 2 times x plus y. This is 2x plus 2y. This is nothing but f of x plus f of y. Okay, so we got the homomorphism condition also. So f is homomorphism. So it is homomorphism 1-1 and on 2. So altogether it implies f is isomorphism. Okay, so the option C is the correct answer, that f is an isomorphism. Okay, so this is also a very trivial question. So we can, if you have doubt, please ask. We will go to next question. Find the index of 3 in set 24. Okay, that means how many cosets are there with respect to this subgroup generated by 3. What is this? Here H is the 3 and G is set 24. Okay, so the question is, what is the index of H in G? So how many cosets are there? Okay, now first we will see how the problem can be solved. First we will see what is the subgroup 3. Subgroup 3 means first the subgroup generated by 3. Okay, so first we will take 3 and add 3 plus 3, 6, 9. So every time what we are doing is set of all 3 power n. Here power means operation is addition. So 3 plus 3, 3 plus 3 plus 3, like that we will go. So 9, 12, 15, 18, 21, 24. 24 means in set 24 it is 0. So this is our subgroup 3. Now we will consider all the possible cosets. Here what is not in 3? 1 is not in 3. So we will take an element which is not in 3 and we will add with that from the left side. So what we will get? 1 plus 3, 1 plus 6, 1 plus 9. So each element will be added by 1 on the left side. So what we will get? 4, 1 plus 3 is 4, 7, 10, 13, 16, 19, 22 and 1. Okay, so this is the cosets 1 plus 3. This is what we are usually notated by AH. Okay, now again we can say 0 and 1 already there in these two groups. Okay, 0 in the first one and 1 is in the second set. This is not a group, this is just a set. Okay, now what we can write? 2 plus 3 we can write. 2 plus 3 means We are adding 2 to the first group 3. Okay. So what we will get? 5, 8, 11, 14, 17, 20, 23 and 2. Okay. Now, does there exist any other coset other than this? We got 3 cosets now. Now, my question is, can you find any other coset, or whether does it covered all the cosets? Maybe if you are observing, yeah, it covered all, very good. So, if you are observing, what you can see in the first set, we have some 8 elements, correct? 8 elements is there. In the next set, we have some distinct 8 elements, correct? Distinct 8 element which is distinct from the first set. So, in the third, again we have the distinct 8 elements which is distinct from first and second set. Okay. Now, again if we are doing, next possibility is 3 plus 3. What is 3 plus 3? It is same as 3. We are just adding, means what it will start with 6, 9, 12, 15, 18, 21, 3, 0, 0, 3, like that it will come, correct? So, it is just same as the earlier one. So, we have only 3 cosets with respect to this one. Okay, so what is this GH, number of cosets of H in G? This is 3, which is same as mod G by mod H in the finite case. What is mod H? That is cardinality of H is 24 and cardinality of G is 24 and cardinality of H is 8, which is same as 3. Okay, so this is how we find the index of a subgroup in G. Now, next, let me ask one question. Define phi from R to Z under addition. That means both R and Z is under addition groups. Okay, it is defined as phi of x equal to greatest integer of x. Okay, so is phi a homomorphism? So what is the greatest integer function? You know that? For example, what is greatest integer? 5.5. Is the greatest integer? The greatest integer less than or equal to 5.5. That is 5. Okay. Good. What is 2.9? 2. Okay. What is 3? Greatest integer 3? 3. Okay. So I hope the thing is clear. So the greatest integer means the greatest integer less than or equal to the given number. Okay. Consider all the lesser integer than the given number. Out of that, which is the greatest one. Okay. Now the question is given as phi is given from R to Z. Obviously it is well defined now, because if I am taking any real number, it is mapping to the integer only. Okay. Under greatest integer, it is going to integer function only. So R to Z only, it is very well defined. Now the question is whether it is a homomorphism. That means whether phi of x plus y equal to phi of x plus phi of y. You can just like check with some suitable example and then any idea? Or I will give you a hint that it is not a homomorphism. For that, what we need, phi of x plus y and phi of x plus phi of y are different. So you have to suitably find x and y such that phi of x plus y not equal to In this way, you need to find the x and y suitably. Can anyone tell? It is like just an easy example. Any possibility you can try such that this condition is satisfied. I mean, this inequality. Okay. Give me 2.6 and y equal to 0. X equal to 1.4. Okay, then y equal to x is 1.4. What y you can take? Y equal to 2.6. Let me check. X equal to 1.4 and y equal to 2.6. So what is phi of x plus y? So what is x plus y? X plus y means equal to 4, right? Okay. So phi of x plus y equal to phi of which is 4. Now phi of x plus phi of y we need to consider. Phi of x is phi of 1.4. So it is 1. Phi of y is 2.6 means 2. So it is 3. So these two are not equal. So this example will work. So you need to choose suitably such that both the sum of this point value should exceed 1. Okay. When we add separately, it will be removed. But if we are adding together and then one point will be more in case of phi of x plus y. One point will be less in phi of x plus phi of y. Okay. So in that case, we got phi is not a homomorphism. Okay. Now the next question is phi from R to R star. What I am saying is R is under addition, R plus and R star under multiplication. Okay, given us phi of x equal to 2 power x. Is this a homomorphism? Okay, we can do very quickly. What is phi of x plus y? Because in the first group R plus it is addition. Okay, so it is 2 power x plus y. What is this? 2 power x into 2 power y. So this is same as phi of x into phi of y. Here the operation is multiplication. So we need to suitably choose and interchange the operation. Okay. So this is a homomorphism. Okay. Okay. Now one more question in homomorphism only. F from Z under addition to R plus under multiplication. Okay. And given f of 3 equal to 1 by 3. Then f of 9 equal to what? Okay. And f is a homomorphism. It is given. Otherwise you cannot do anything. Okay. F is a given map from Z plus to R plus under multiplication with the f of 3 is given as 1 by 3. Then what is f of 9? If f is given as a homomorphism. You can do the calculation. The similar kind of question we have done already. So you can do the calculation quickly. What is f of 9? What we have is only f of 3. Value of f of 3 only we have. So we need to write 9 in terms of 3. Okay, using the operation addition, because addition is the operation we have in the first group. How we can write f of 9 in terms of 3? We should use just the addition. It is f of 3 plus 3 plus 3, right? Okay. Now, since f is a homomorphism, we can use the condition of homomorphism. What is this? F of 3 into f of 3 into f of 3. You should not write f of 3 plus f of 3 plus f of 3. The reason is, in r plus dot we have the operation multiplication. F of 3 into f of 3 into f of 3. Now, what is this f of 3? It is given 1 by 3. 1 by 3 into 1 by 3 into 1 by 3, which is 1 by 27. So it is just like expanding the 9 in terms of this value, like whatever given, and then just doing the, like just using the homomorphism property and doing the calculation. That's it. It's clear? Any doubt? Okay, now we will do one last question and we will stop. If H, K are normal subgroups of G and H intersection K is given as the trivial group. Okay. Then HK equal to KH for all H in H, for all K in K. So this we need to prove. Okay, this is the question. If H and K are normal subgroup and H intersection K is just the identity, what we need is HK equal to KH for all H in H and for all K in K. So this is what we want to prove. So how we will start with this? HK, H inverse, K inverse. Okay. HK, H inverse, K inverse. Okay. Where does the first element belongs? H into K H inverse, K inverse. Where does this belong? Okay, what we know? H belongs to H, we already know. What about K H inverse, K inverse? This also belongs to H, right? Because H is a normal subgroup. When H is a normal subgroup, we already proved that X inverse belongs to H for all X in G. Here we are taking K from K only, but still the result holds. So these two element belongs to H means the product also belongs to H. Similarly, okay, this belongs to K. Since K is a normal subgroup, given H and K are normal subgroup, and this also belongs to K. So this belongs to K also. So what we got, we are taking the same element here, just we have multiplied in a, like the order just changed. Okay, the bracket is just changed. So what we got is H inverse K inverse belongs to H intersection K. It belongs to H and it belongs to K. So it belongs to the intersection. And what we got in the question, H intersection K is just the identity element. So if some element belongs to H intersection K, which is just the identity, so what we can conclude, HK, H inverse K inverse equal to just the identity. Okay. Now what we will get a HK, H inverse K inverse into K into H. We are multiplying with the KH on both sides. So first we will get this as identity, and then the next step these two. We will get identity. So what is this? HK equal to KH. So we are choosing arbitrary element H and K from the subgroup H and K. Okay. So we got, if H and K are normal subgroup, we completely use the normality. If it is not there, we cannot do this two steps. Okay, and H intersection K equal to identity, that also we used because we equated this with the identity. Okay, so from that we have just like rearranging KH, and then we got HK equal to KH for all K in K and H in H. So the given statement is also true, that means we proved that. Okay. Okay, so I think let's stop for today. It's like there are some more concept in the week. Whatever, it is not that difficult if you are going through the concept and again do the some problems, so many problems, so it will be easy for you. Actually this abstract algebra is over this week. From the next week onwards it is starting linear algebra. Linear algebra which starts with vector space, linear transformation and all. That's also not that difficult concept, you can follow very easily. So now we are just giving an introduction to abstract here, and we are stopping that introduction here, and the next thing is then introduction to linear algebra. So from next week onwards we will see the questions related to the linear algebra. Okay, so it is all for today. We will meet in the next week again, the same time, same day. So thank you everyone for attending. Yeah, thank you. Let's close the session. Good.
Thank you.